Welcome back, it's Professor Elliott again, and this is a lesson video on the Darlington amplifier. Okay, so please go print a copy of your circuit, and then we'll have you can use that as something to work from. Okay, so go do that. Go do that now, please, and I'll be with you in a minute. Okay, welcome back. So you can see that we have a arrangement where we have two cascaded transistors. So this is the Darlington amplifier or the Darlington pair amplifier, same thing. Because of that, we have a beta AC amplification effect. So that means that the resistance looking into and the impedance as well, looking into the base is going to be very high. So we can just make some simplistic assumptions. So we don't have to go ahead and solve the VTH and the Thevenin like we did the same degrees that we did before with the other amplifiers. So anyway, let me just go and erase that. I might need to come back. Okay. Notice that the impedance of R3, which is the load, is very small. And so the Darlington amplifier can be used to drive low impedance loads. So we do need, so RTH, R1 parallel with R2, as per usual, 6.67 k ohms, okay, which is just those two in parallel. Okay, VTH, so this is so this is V2, which is also VTH. And again, it's just the voltage from the base down to the ground. So it's going to be R2 over R1, R2, VCC. So that's going to be 20 divided by 30 times 20 is 13.33 volts. Okay. All right. Solving emitter voltage VE. Okay. So we're going to forego calculating IB like we normally would, because we know that the input impedance is so high. So this is a very good approximation. So if we know the base voltage there, we can just simply minus that. That will give us the emitter voltage there. So it's the base voltage, which is V2, which is VTH, minus 2 VBE. So that's 13.33 minus 1.4 minus 1.4 equals 11.93 volts at the emitter. Okay, so we know this is 11.93 divided by RE, that gives us emitter current. Okay, so IC, which is of course is equal to IE, equals VE divided by RE. So that's 13. Sorry. 11.93, 12 ohms. So that equals 900. Oops, what happened there? Sorry about that. Not sure what happened. And we were on IC, right? All right. Sorry, we have to pick up where we left off. So IC again was equal to IE. So it equals VE divided by RE. So that was the 11.93, 12 ohms. It's 994. Okay, so it's a fair bit more current than we've seen up till this point. It's characteristic of these amplifiers. Okay, so all right, should have that down. Okay, so according to the AC model, on second thought, okay, so we know that this current is IE. We know that current IC. So we're really only concerned with Q2 because Q2 is the one that's controlling the load current. Okay, is that the voltage VCE here. So let's calculate that, and let's calculate the power dissipation, and then we'll do the AC model. So I think I want to add that in. Okay. So let's go and then just erase this. Okay. Okay, so let's solve for VCE. VCE is equal to VCC minus VE, and this was 20, minus 11.93, 20 minus 11.93 equals 8.07 volts. Okay, so that's going to be the voltage there. And now I'm going to erase that. Okay, I want to solve the approximate power dissipation of transistor 2 equals IC, just to give you an idea here. And this isn't factoring in the AC current, this is just the DC current. But anyway, so that's going to be the 994.44 milliamps times 8 volts times 0.99444 equals, okay, 8.03 watts. Right, so it's a fair bit of power. You're probably looking at a 10 watt transistor minimum, so it's going to be quite a bit larger than the ones in your kit, but anyway, it kind of gives you an idea. Okay, all right. So the AC model. The AC model. Let's go back again to that. Okay, let's get rid of all the stuff we don't need. Okay, so again, the procedure is that we throw this away, short that to ground, replace with a jumper wire, replace with a jumper wire, and then redraw. So what we end up with essentially is like that, okay, like that. VO, Z out, collector goes to ground, like that. Z in base. RTH and Z in. There's handouts on this as well. Okay, so that's the AC model. So Z out is going to be RE in parallel with R3. So I want 12 in parallel with 10. So that's 5.45 ohms. Okay, so that will be RE in parallel with RL, which is R3. So that's going to be 12 parallel with 10 equals 5. Okay, so that's quite a bit lower than any of the ones we've seen to date. Ohms. Z in base is going to be beta AC times Z out. Okay, R prime E is going to be down in the milliohm range because of the high IC, so we're just going to ignore that. Okay, and let's set beta AC equal 110 times Z out 5.45. Okay, Z in base equals 600 ohms, and Z in equals RTH in parallel with Z in base. So that equals what? 6.67 k ohms in parallel with 600 ohms. So 1 divided by 0.6 is 1 divided by 6.67. So that equals roughly 550.48 ohms. Okay, I'm just going to write that down. Where's that at? All right. So, yeah, so we're ignoring R prime E. So that's going to be the input impedance, and so that's just reflecting Z out, reflecting that to Z in base, and then paralleling these two to give us Z in. And yeah, so now the voltage gain AV, again, that comes off the emitter, so the input and output are in phase. Exactly, it's going to be Z out divided by R prime E plus Z out. Okay, so it's really going to be, again, a slight attenuation. It's not intended to provide gain. It's intended to drive a low impedance load. Okay, but if we simply ignore that because that's going to be so small, we can simply say AV is approximately equal to 1. Okay, so that means then that the output and input voltage are almost the same. Okay, so I didn't give us an input voltage, but anyway, the formula must be AV if you knew the output voltage divided by Vin. So therefore, VO equals AV times Vn. So Vn is approximately equal to VO, and the two waveforms, not to scale or anything, okay, are going to look something like that in phase. Okay, so that's it. Catch you later, guys. Okay, bye-bye.